some of them not here.
Okay, I think let's get started. So welcome to our seminar today. So today is our great pleasure to welcome Professor Katy Craig from UC Santa Barbara. Katy, her research interest is majorly focused on partial differential equations and optimal transport. She received her PhD from Rutgers University in 2014, after which she spent 1 year at UCLA as an NSF Mathematical Sciences postdoc fellow, and 1 year at UCSB as a UC President postdoc fellow. In January 2020, very new, she was awarded an NSF Career Grant, very prestigious award, to support her work on optimal transport and machine learning. Katy, please.
Well, thank you very much for that introduction and for inviting me to speak. Like I've already confessed, this is my first time using WebEx, so please at any point feel free to unmute yourself and jump in and correct anything wrong that I'm doing with the technology. As has already been said, I guess, today I'm going to be talking about connections with partial differential equations. In particular, the title of my talk today is on graph clustering dynamics from spectral to mean shift via Fokker Planck. And this is based on a joint work with Nicolás, García, Trillos, and Dejan, Slepčev. So here's my plan for today's talk. I'm going to start by explaining our main goal, which was to define an appropriate notion of Fokker Planck equation on a graph. So I'm going to remind everyone, what is the Fokker Planck equation? Why is this equation just ubiquitous across the sciences? And why did we want to define it on a graph? And we had three main motivations. One is this could be useful in sampling. Two, this could be useful in numerical analysis. And three, this could be useful in designing and kind of analyzing clustering algorithms for data. And in particular, that last motivation, the connections between a graph Fokker Planck equation and clustering algorithms for data, is going to be the main focus of my talk today. The second thing I'll talk about today is explaining this connection between Fokker Planck type equations and clustering algorithms, and in particular, how a Fokker Planck equation on a graph could allow us to understand the role of density versus geometry in clustering algorithms and design new algorithms that smoothly interpolate between clustering on a data set's density and clustering based on the geometry of a data set. Once I've kind of explained our goal and our motivation, I'll move on to say how we did it. And in particular, our strategy for defining a type of Fokker Planck equation on a graph was to use its Wasserstein gradient flow structure. So I'll say a little bit about what it means for the Fokker Planck equation on Euclidean space to be a Wasserstein gradient flow, and how this same structure exists in the setting of a graph, and we can use it again to define an appropriate notion of Fokker Planck equation on a graph. Once we've done this, I'll close with several numerical examples that show how this type of equation can be used in data clustering, and understand the role of kind of diffusion or lack thereof in the clustering performance based on kind of density or geometry. Okay, so this is my plan, but like I said, I'm going to start off by explaining this main goal and the motivation for this in the graphical setting. Okay, so first, what is the Fokker Planck equation on Euclidean space? So if we have a curve rho, we're thinking of rho as a curve in the space of probability measures. So it takes in times, and at each time it spits out a probability measure on d-dimensional Euclidean space. And we'll say that such a kind of a probability measure evolving in time solves the Fokker Planck equation if it satisfies this initial value problem in the weak sense, in the duality with C infinity compactly supported functions. So we see this is basically just saying that the time derivative of rho equals Laplacian of rho. So here we have a bit of diffusion plus a divergence of rho times gradient of V, where V is some fixed external potential. So we'll call this the drift term in the Fokker Planck equation. so maybe the easiest way to see why the Fokker Planck equation is ubiquitous across the sciences is thinking about these dynamics from the microscopic perspective. So if you consider this stochastic differential equation, so now this is saying we have a random variable that's evolving according to Brownian motion and also steepest descent of this external potential, then it turns out that the law of this stochastic differential equation exactly solves the Fokker-Planck equation. And to me, this seems like something that is extremely natural and would show up in a lot of cases. Like basically anywhere where you're doing gradient descent, so you're trying to kind of do some sort of minimization of your external potential V, but there's a little bit of noise, this will lead to something like a Fokker-Planck equation. Okay, and so this kind of happens everywhere. One important place that it happens, and that has been kind of a relevant application in recent years, is in sampling. So, for example, it turns out that is under suitable assumptions on your external potential V, a steady state of the Fokker-Planck equation is given by this global Maxwellian. And if you know that your external potential V is strongly convex, then solutions of this equation will converge to this. This will actually be the unique global equilibrium, and solutions of this equation will converge to that global equilibrium exponentially quickly in time. And so this is really important in sampling because there they choose their potential V so that this steady state is the measure they want to sample from. And then they know by the theory of the Fokker-Planck equation that however they initialize their microscopic dynamics, these dynamics are going to get sucked into this steady state, allowing them to sample from the desired measure. Okay, so this is another reason that the Fokker-Planck equation is so kind of well studied in many contexts. And then the last key fact about the Fokker-Planck equation that I'm going to use in today's talk is that solutions of this equation are characterized by the fact that they're a Wasserstein gradient flow of this energy. In other words, rho is a solution of this equation if and only if it makes this energy small as quickly as possible with respect to the Wasserstein structure. So it kind of dissipates this energy as quickly as possible. And so this structure is exactly what we're going to use when we define a Fokker-Planck equation on a graph. We're going to mimic this energy dissipation property of the PDE. Okay, so it's maybe classical why the Fokker-Planck equation is so important in the continuum sense. And one maybe brief notational remark I should make before I leave the continuum case is that I'm going to do a little abuse. And sometimes when I'm thinking of rho as a measure, and if it is absolutely continuous with respect to Lebesgue measure, I'm going to use the same symbol rho for both the measure and its density. And then more generally, once I start talking about probability measures on a graph, I'm going to use the same symbol for both the measure and the density of that measure with respect to the data distribution. So this is just so I don't have to double the number of symbols in this talk, which I think makes things very confusing. But if at any point this convention becomes confusing, I'm happy to specify which is the measure and which is the density, things like this. Okay, so here we have the Fokker-Planck on the continuum. Why do we want to come up with an analogous equation in the graphical setting? So first, I already explained why the Fokker-Planck equation is so important in sampling on the continuum. Similarly, if I wanted to sample a probability measure on some large graph, following some sort of Fokker-Planck dynamics on that graph would be a natural choice, and one that you could probably get some sort of provable convergence guarantees. A second reason for defining a notion of Fokker-Planck equation on a graph comes from a numerical analysis motivation. So what if instead of wanting to solve the Fokker-Planck equation on Euclidean space, I wanted to solve the Fokker-Planck equation on some complex manifold? Something that's really nice about graphs is that they're very geometrically expressive. And so if I approximate some complex manifold by a graph, and then I solve the Fokker-Planck equation on that graph, one could hope for some kind of consistency result that shows that the this discretization converges to the Fokker Planck equation on the continuum manifold. And then lastly, the motivation that I'll focus on today is for designing new clustering algorithms and analyzing existing clustering algorithms. And especially for this third motivation, I'm actually going to be thinking of a slight variant of this classical Fokker Planck equation. I'm going to introduce an additional parameter beta. So I can interpolate between, we see beta equals 0, we have no drift and pure diffusion. And beta equals 1, I have no diffusion and pure drift. And the role of this parameter beta in the behavior of the clustering algorithm is, something that we're going to explore later in the talk. Okay, so in summary, the goal of our project was we wanted to define a Fokker Planck equation on a graph. It was very important that our graph notion, our graph analog of Fokker Planck equation was a linear equation. Here we see, of course, the classical Fokker Planck equation is linear in row. There's plenty of ways to define a nonlinear Fokker Planck equation on a graph, but I would argue that the additional computational complexity that introduces is a huge barrier. And so we wanted to make sure that we captured this key property of the continuum Fokker Planck equation. And furthermore, we wanted to make sure that our Fokker Planck equation on a graph really allowed us to interpolate between pure diffusion, beta equals 0, and pure drift, beta equals 1. And you'll see why in our examples that, in fact, taking beta very, very close to 1 gives some good performance in the clustering context. So this is something that we wanted to be able to preserve at the discrete level. We didn't want any sort of deterioration of the dynamics in either of these limits as beta goes to 0 or 1. Okay, so I've told you that a graph Fokker Planck equation is useful in designing clustering algorithms, but why is that the case? And what is this connection between, on one hand, the diffusion and the drift in the Fokker Planck equation, and this dichotomy between clustering based on density of a data set or clustering based on geometry of a data set? Okay, so first, I will tell you just a little bit at a high level, what do I mean by a clustering method in the context of today's talk? So I'll assume I'm given some data set, which are just given by some points x1 to xn. So for example, we can visualize this as an example of a data set where the locations of the points are just plotted here in 2 dimensions. Now, if I want, often in clustering, the problem you're trying to solve is you're given all these data points and you're told to divide them into k groups. So for simplicity, let's just say somebody told you to divide this data set into 2 groups. Now, one paradigm for doing this is to cluster based on the density of the data set, in which case clusters are defined to be regions of high concentrations of points separated by areas of low density, and kind of a canonical algorithm for this is the mean shift algorithm. So if I was going to cluster this data set based on density, then a natural approach would be to say, well, this is a pretty low density region right here. So maybe I'm going to call that one of my clusters, and then the bottom the other cluster. So if I had to break this into 2 clusters, maybe that's how I would do it. On the other hand, one could also attempt to cluster a data set based on geometry. And in this case, one thinks of clusters as connected regions of the data set that are separated by bottlenecks. And here, a canonical method is kind of spectral clustering techniques. But if I want to cluster this into 2 groups based on geometry, perhaps I get a different answer. It seems like depending on how you're defining the connectivity, this whole thing here could be one, in fact, the whole thing could be a connected component. And then what I want to say is that my connected regions are separated by a narrow bottleneck. So because this looks like a bottleneck here, maybe I would say that that's one group in my data set and this is another. Okay, so from this toy example, it's clear that there's not always a right answer in terms of how to cluster. In a sense, it could be correct depending on context to either break this into 2 groups based on the density or the geometry of the data set. But instead, this is kind of a modeling assumption that you have to make. Based on some kind of domain knowledge of your data. but something that we were interested in is, so far in the literature, these methods based on density or geometry have been treated as conceptually disjoint. Like, okay, if you're interested in clustering your data, try one mean shift and try one spectral clustering and see what gives you the reasonable results. But we were interested in using a Fokker Planck equation to put these two types of methods into the same mathematical framework and devise a way to smoothly interpolate between them so that you could, cluster maybe a little bit based on geometry and a lot based on density. Okay, so for the sake of trying to put these two things in the same mathematical framework, I'm going to say what a clustering algorithm is at a very high level. I'll say that either a clustering algorithm based on density or a clustering algorithm based on geometry has two steps. The first step is an embedding step, where I apply a function psi to my data set and map it into a new space. And the hope is that we're able to pick this function psi in a really smart way that disentangles my data set, so that in the new space, the clusters are really well separated and grouped together, and that a simple clustering methods, for example, k-means, could easily break them into groups. Okay, so in today's talk, I'm always going to be focused on the design of this embedding map, capital Psi, and I'm always just going to use k-means in the embedded space. So our goal is to use a Fokker Planck equation to design this type of embedding map, which recovers both these kind of density-based and geometry-based methods. And then I'll talk a little bit about at the end about some interesting recent work by Little, McKenzie, and Murphy, also looking at this interpolating between methods based on density and methods based on geometry from a different perspective, but one that will kind of emerge later in the talk. Okay, so in order to see how density and geometry and Fokker Planck are all related, let me begin by talking about density-based clustering methods. In particular, let me talk about the mean shift clustering method. Okay, so how does this method work? How does this identify clusters in a data set? So for mean shift, we have to suppose that our data set is embedded in some Euclidean space. For my simplicity, I'm just going to draw an example where it's embedded on the line. Okay, so we're going to assume that my data points are just points on this line. Maybe I have a bunch of data points there, then maybe I have some in the middle, and then a bunch more over here. Okay, and my goal is to divide this data set into two clusters. So how mean shift does it is it takes a kernel density estimate of your data set. Okay, so if this is my data set, maybe my kernel density estimate is something like this. We'll say for simplicity. Okay, this is kind of a bad picture, but you get the idea. Roughly, there's sort of more data points in the regions of high density of my estimator. Okay, and so I have my kernel density estimator Q hat, and what mean shift does is it takes the locations of each of my data points, each of these x naughts, and it evolves them via gradient ascent of log of Q hat. So why log of Q hat? Well, it just wants to deal with the fact that what if you had a kernel density estimator that had vastly different scales? You want the speed of the gradient flow dynamics to be approximately the same in spite of, maybe apparently very different scales in the density estimator. Okay, so if I evolve these locations of these points by gradient ascent of this, logarithm of my density estimator, what does that do? Well, these points here, they're all going to be moving towards the local maxima of my density estimator. This one will, probably move over there. And these points will all move to this local maxima of my density estimator. So we see that after running these dynamics, this ODE on the locations of my data set, after some time t, they end up at these new points, xit. And we can see that these are, much better separated and better clustered than they were originally. So, the idea is that this embedding map has somehow, going the wrong way, has somehow disentangled my data, and it's now more easy to separate it into two clusters. Okay, so how does this relate to the Fokker Planck equation? We can lift this system of ODEs to a PDE perspective. So it turns out that xi solving this ODE, just being a curve in d-dimensional Euclidean space, is equivalent to saying that the Dirac mass centered at this xi of t solves this PDE in the weak sense. So there's basically just a one-to-one correspondence of solutions of this ODE and solutions of this PDE that are concentrated at a Dirac mass. So at first, this probably seems like an unnecessary complexification of the problem. Why have I gone from this very simple ODE to suddenly a PDE in the space of probability measures? But it's because this will allow us to kind of this will be a more flexible approach that we can also bring in clustering methods based on geometry. So just bear with me for the moment. So because this PDE perspective is going to be important in today's talk, I want to slightly redefine my embedding map to leverage this perspective. And how I'm going to write that is I'm going to use this notation of the semigroup operator. So this is just sort of a shorthand way to write solutions of this PDE, this initial value problem, that emphasizes the dependence on the initial data. In other words, what ST of rho naught means is you take the initial condition rho naught, and then you solve this equation up to time t, and you look at that solution. Okay, so this is the semigroup notation. And now using this notation, I'm going to tweak my definition of the embedding map. And I'm going to say that for each point in my data set, what I want to do is I'm going to map that, instead of mapping it to a point in d-dimensional Euclidean space like I did up here, I'm actually going to map it to a probability measure. Which probability measure? Well, it's just the Dirac mass kind of centered at that point. Or in other words, I can think of this as saying, I start off with some data point, and then what I do is I look at the Dirac mass centered at that point, and then solve this drift equation up to time t. Now, I haven't said anything about this time t. Clearly, this choice of time t is important. If I don't choose this time t big enough, then my points might not have enough time to evolve close to the local maximizer of my kernel density estimate. But in general, this is just treated as kind of a user-defined parameter, but something that clearly has a lot of bearing on the results of the clustering algorithm.
So, Katy,
okay. Yes.
Quick question, just clarification.
Yes.
So the V here, I assume, is the log Q, right? Or minus.
Thank you. Yes, exactly. So here, my choice of V is given by negative log Q hat.
But as you mentioned, right? So if Q is strongly convex, this thing converges like exponential fast. But most cases is not strongly convex. So
yes,
which means P is, I mean, the dynamic converts to whatever you prefer is very slow.
Right? So I guess
T.
Say it again.
Yeah, I mean, if the dynamic converges to the density you prefer, will be very slow. So you have to choose a like very huge. It won't be exponentially decay. You have to choose a very big capital T. Is that?
Yeah. Well, and I guess on one hand, it's sort of. I mean, yeah. Here, as you say, kind of in contrast to what they hope for in sampling, here we're in general going to be interested in kernel density estimates that have many local maxima, and so consequently their logarithm is not going to be strongly concave, and sort of negatively logarithm is not going to be strongly convex, and that's kind of good, because if otherwise this wouldn't be a very good. For clustering, we really want it to have lots of local maxima, that different parts of the data set are drawn towards different local maxima, and this allows us to disentangle the data set. But I think your point is definitely right, that, for example, if, because of this, what if we started with some data element that was, in this flat region here? Well, first of all, if this was, If this was completely flat, then it would just stay there for all time. But maybe even if it was just a slightly bit to the right, it could take an extremely long time to go towards this local maxima.
Yeah.
So this is something that, yes, I think this is actually a really interesting question in this problem, especially once I start bringing in the kind of the geometry based clustering methods and which kind of in particular sort of bringing a diffusion operator into this equation. And so I think coming up with a smart way to choose your time scale so that you could get guarantees about the clustering of your algorithm is an interesting open problem. And it relates to somehow the formation of metastable states in the Fokker Planck equation. So we know that in this context, we're going to be interested in external potentials that are not strongly convex. And so, we want the formation of these metastable states because that's allowing us to disentangle our data. But understanding the time scales at which those form and eventually may merge is something that I think is not fully understood in this clustering context. But to me, this is a very interesting direction. It's like, yeah, how could, can we kind of, by looking at the eigenvalues of some of these operators, say something about the timescales at which metastable states form, and then we'll know, for example, if we run it up to some very, very long time scale, then maybe eventually, especially if we have some diffusion, all of the clusters will merge. But if we run it up to shorter time scales, we would pick out larger numbers of clusters. So anyway, this is, I think, a very good point, but one that I think is not fully understood in this context.
But the other thing, the good thing is that your density is actually starting from something very close to the Q hat, right? Because Q hat is estimation of that. It's not from something.
Well, let me emphasize that actually what it's doing is my initial condition is a single data point. So it's a Dirac mass at a single point in my data set, not at the, so in fact, it's very concentrated, not this kind of continuum density estimate.
I see, thanks.
So for each point in my data set, I'm starting at a Dirac mass and running this drift equation forward in time, and that tells me how to embed that single point.
Thanks.
Thank you. Okay, so this is sort of, now I hope it's a little bit more clear to see how this sort of density-based clustering mean shift connects to at least the drift part of the Fokker Planck equation. How does the geometry perspective of clustering connect to the diffusion part of the Fokker Planck equation? So I'll talk about this in the context of spectral clustering methods, in particular from the perspective Coifman and Lafon introduced in their paper on diffusion maps. So here we again have some collection of data points, x1 to xn. We no longer need them to be embedded in some d-dimensional Euclidean space. We have a weight function, symmetric weight function defined on the product of x and x that tells us in some sense how similar two data points are. This gives us a notion of a connected graph, a weighted graph. A weighted graph, which I'm going to assume in today's talk is always connected. For any function on the nodes of my graph, I can define a notion of graph gradient, which is defined on the edges. You have to kind of prescribe two nodes to evaluate the gradient. And then dually, for any function on the edges of my graph, I can define a notion of graph divergence. And from a mathematician's perspective, once you have a divergence and a gradient, it's not too surprising that you can come up with a Laplacian. This is known as the unnormalized Laplacian operator and can also be expressed in terms of the degree matrix, a weight matrix of the graph. But in today's talk, I'm going to be focusing on a slight variant of this Laplacian, which is known as the Coifman-Lafon Laplacian. And to stay at a high level, we'll just say this is again defined in terms of kind of appropriate powers of degree matrix and weight matrix. So once you have all these matrices on your graph, you have the sort of graph Laplacian matrix. How does it help you cluster your data? So the spectral perspective on this is that you take this matrix, you take this sort of graph Laplacian, and you look at its eigenvectors and eigenvalues, and you define your embedding map as follows. So you take a data point, and where you map it to is the value of the eigenvectors at that point, weighted by the size of the eigenvalue, raised to some power m. And m plays exactly this, and this is again a user-defined parameter that plays exactly the same role as the time parameter in mean shift. And I'll say a little bit more about that in a second. At first glance, like this spectral perspective seems very different from mean shift. We weren't talking about anything. We were talking about ODEs there, not eigenvalues and eigenvectors. So what is the connection? And this was, kind of this sort of connection between spectral clustering methods and dynamics was due to Coifman and Lafon's influential work. They observed that this graph Laplacian here is in fact, or I guess it's negative, is a transition rate matrix. And what that means is that its entries are non-negative off the diagonal, and they sum to 0. And if you're a transition rate matrix, what that means is that if you look at the associated ODE, and so in particular, you could replace this right-hand side by rho TQ for any transition rate matrix Q. Now, this is just, we think of this as a ODE. My initial condition is some mu, which I'll think of as a probability measure, or more specifically, a probability vector on the graph. So it's just a vector within nodes where all of the entries are non-negative and they sum to 1. And then I can, solve this ODE where it's conventional to write multiplication in this context of my vector and my matrix. And if Q is a transition weight matrix, then the fact that my initial condition is a probability vector means that for all time greater than 0, my solution of this ODE will remain a probability vector. It will remain non-negative and its entries will still sum to 1. And so if you remember, this was kind of an important thing about the Fokker Planck equation as well. That could be framed as the evolution of a probability measure. The Fokker Planck equation is positivity preserving and mass preserving in the same way here. Okay, so this is maybe suggesting already that there's going to be a connection. Again, this sort of Markov chain describes the evolution in the space of probability measures. And again, we can use semigroup notation as a shorthand here to emphasize the dependence on the choice of the initial condition. We'll say that the solution of this continuous time Markov chain at some later time t is, okay, I can either write it in terms of right multiplication with the matrix exponential, or I can write it as saying, I just take my initial condition and then I run the semigroup. I run these dynamics up to time t. And so the kind of amazing thing that Coifman and Lafon observe is that up to a change of basis, this embedding operator, psi, is exactly the same as taking your data point xi, looking at a Dirac mass at xi. Now this is okay, this is a Dirac mass on the graph, so this is a probability vector, and running these dynamics up to time t. Okay, so now things look very similar as with the mean shift. In both cases, to figure out how to embed our data point, we look at a Dirac mass centered at that data point, and we run some dynamics on it up to time t. But there's still one big difference here, which is these dynamics are still just occurring on the graph. This is still just sort of matrix vector multiplication. So our space is still discrete. This is unlike mean shift, which is operating kind of embedded in d-dimensional Euclidean space. So this is sort of like a discrete sort of graph heat equation with this version of a graph Laplacian. But we can look at the continuum limit of it. And this is something that's been studied extensively by many authors. And the type of result one can often prove in this setting is that if your data points are given by IID samples of some underlying distribution Q, And the weight matrix is given kind of in terms of their proximity in some embedded space, where we can think of eta as, for example, being a Gaussian with variance epsilon. So it's something that's larger if x and y are close together and small if x and y are far apart. Then as the number of samples goes to infinity, and as long as your variance of your Gaussian goes to zero sufficiently slowly, then this dynamics of this graph heat equation converge exactly to this equation. And so now we're back to something that's a PDE, something that's framed on the continuum space, and that we can do an apples to apples comparison with the mean shift. Now, when you first look at this, you might say, well, great, Katy, by looking at this continuum limit of the graph heat equation, you have found a Fokker Planck equation. You know, we have time derivative, Laplacian of rho. I guess this is, could be a bit more general Laplace-Beltrami operator if our samples of Q and Q was defined on some manifold. And then again, we have our drift term here. So aren't you done? Like, isn't Coifman and Lafon's graph Laplacian and that the associated graph heat equation exactly a graph version of the Fokker Planck equation? But if we look at it a little bit more carefully, you'll see that there's two ways in which this is not exactly what we were looking for. So the first thing to observe is that let's rescale this equation in time so that we really can interpolate between pure diffusion, beta equals 0, and pure drift, beta equals 1. So we can see that pure diffusion, beta equals 0, corresponds to sorry, I'm saying this in the backwards way. Pure drift, beta equals 1, corresponds to sending alpha to negative infinity. And if alpha going to negative infinity corresponds to sending time to plus infinity. So unfortunately, while this is a Fokker-Planck equation, if we want to look at the limit as diffusion vanishes and we have pure diffusion, our dynamics degenerate in that limit. You're kind of having to send time to plus infinity at the same time as you're removing diffusion. So you kind of lose dynamics in the limit. So that's one downside of this existing notion of Fokker-Planck equation, is we lose this ability to smoothly interpolate between pure diffusion and pure drift. And then a second drawback is that here, kind of this relates to Rangier's question, which is that the choice of V here is predefined, kind of baked into the definition of this matrix, this notion of graph Laplacian, is that our external potential has to be of this form. So it's not like we have flexibility to pick different choices of external potential, as would be very important, for example, in kind of a sampling or numerical analysis motivation. Okay, so just to summarize, this wasn't quite what we wanted because there's only one choice you can make for external potential that's baked into the definition of L, and it degenerates as beta goes to 1. Okay, so on one hand, we see how these existing methods, mean shift and diffusion maps, sort of relate to a Fokker-Planck equation. Diffusion maps is kind of this type of Fokker-Planck equation. Typically, alpha is chosen to be something between 0 and 1. And mean shift is, what you would get if you were allowed to send beta to 1 and kind of remove all of the diffusion. Okay, so how can we go from this motivation of seeing this connection between Fokker-Planck equations and clustering and to find a real Fokker-Planck equation on a graph that we can truly get the beta equals 0 and beta equals 1 case and understand the effect of these parameters on the clustering behavior? So like I already said, we're going to do this by using this Wasserstein gradient flow perspective for the Fokker-Planck equation. So since I want to make sure I leave plenty of time for my numerics at the end, I'm just going to go through this part somewhat quickly. The Wasserstein distance, this is something that was On one hand is a very old problem, was originally posed by Gaspard Monge in the late 1700s. On the other hand is something that's attracted more interest in recent years. It's a way to define a notion of distance between two probability measures, mu and nu. Right now I'm thinking of just probability measures on Euclidean space, in terms of how much effort it would take to rearrange mu to look like nu. This is the Monge formulation of the problem, the classical formulation of the problem. But our more modern formulation of the problem is due to Benamou and Brenier. And here we say that the Wasserstein distance between mu naught and mu1, or here I actually wrote the squared Wasserstein distance, so I didn't have to put a square root on the right-hand side, is defined in terms of this minimization problem. Basically, what we do is we look at all solutions of the continuity equation for any choice of velocity field that start off at time 0 at mu naught and end up at time 1 at mu1. So this is basically, if I have some mu naught and mu1, I look at all ways of flowing between them that conserve mass. That's another way to say all solutions of the continuity equation. And what I want to do is I want to find that solution and that choice of velocity field that make the kinetic energy as small as possible. So this is the sense in which we're looking at rearranging mu naught to look like mu1 with the least amount of effort. This is kind of our measure of effort, is kinetic energy. So in this way, we can kind of define the Wasserstein metric on Euclidean space. And, you know, once you have a metric, you can also define sort of weak notions of gradient flows. In particular, a gradient flow is just an evolution of a probability measure that makes some notion of energy get small as quickly as possible with respect to Wasserstein perturbations. And we can see that the gradient flows of each of these energies give rise to different types of PDEs, though most importantly in the context today is the Fokker Planck equation. And so how can we take this theory that's well understood in the Euclidean context and bring it to a graph? And the funny thing here was the difficulty wasn't seeing how can we take it over to a graph, or does there exist a way to take it over to a graph? The problem was there were so many different ways to take it over to a graph. How can we choose between them? And so to define, in fact, yeah, like I just said, over the past 10 years, there's been lots of different works defining appropriate notions of Wasserstein metrics on graphs. They all can be put in the unified framework in this way, very similar to the Benamou-Brenier formulation of Wasserstein distance on Euclidean space. Basically, if I have two probability measures on a graph, and I'm interested in their Wasserstein distance, I look at all of the continuity equations that start off at one and end up at the other, all different choices of density, rho, evolving in time, and all different choices of velocity kind of driving that evolution. And I pick the one with smallest kinetic energy. But one thing that I kind of haven't said here, you know, I have already told you what the graph divergence is, and I have already told you what sort of the weight function on the graph is. So a lot of these things already make sense. But I haven't told you what these rho bars are. And in fact, this is the key question in terms of discriminating between all of these different notions of Wasserstein metric on the graph, is what choice of interpolation function to make. In the short version of why this problem arises in the graphical setting, but not the continuum setting, is that, as I already mentioned, the divergence operator on a graph, this is something that operates on functions on the edges and spits out a function on the nodes. So we need to apply our divergence operator to something which is a function on the edges of the graph. But our measures, rho naught and rho 1, we were thinking of these as measures on the nodes of the graph, probability vectors on the nodes. So how, in order to properly define a graph continuity equation, we need some way from going from our rho, that's a function on the nodes, to a rho bar that's a function on the edges. And there's lots of different ways to do that. I mean, probably the simplest way one could think of do that would be just to take an arithmetic average. If I want to define a rho bar on an edge, I just average the values of rho on the two nodes that edge connects. The good news is this, it does induce a true notion of Wasserstein metric on the graph. Bad news is that the kind of gradient flow structure with respect to it is not so nice, and kind of in some ways cannot even be positivity preserving. So you can start off with something that's a flow in the space of probability measure, and then suddenly at some time you leave the space of probability measures. Okay, and that's bad. That wouldn't give us a notion of Fokker Planck equation that we felt captured what is going on in the continuum. Another case that has really nice kind of geometric interpretation is the logarithmic interpolation. This does induce a true Wasserstein metric on the graph, but unfortunately, in the absence of diffusion, the support of the gradient flow can't expand. And this is really bad if you're thinking about what would happen with mean shift on the graph, because there, our initial condition is just a Dirac mass at the point, and it's supposed to just evolve by drift around the graph. But if the support can't expand, then if your initial condition is just started at, only has support of a single point, it will just stay at that point for all time. So this sort of had no hope of being able to capture the right dynamics in the absence of diffusion. And so instead, we settled on this upwinding interpolation. The good news is that it overcomes the two problems I mentioned here. The bad news is that the corresponding Wasserstein metric is actually not a metric, it's a quasi-metric. So the effort of going from rho naught to rho 1 is not necessarily equal to the effort of going from rho 1 to rho naught. But you can still define an appropriate notion of gradient flow. This notion of gradient flow is great for the drift part of the Fokker Planck equation. But if we try to do just the gradient flow of the entropy and expect to get something that would give us like the diffusion part of the Fokker Planck equation, you get something that's nonlinear. And this is, again, bad news. Like I said at the beginning, we don't want to come up with some version of the Fokker Planck equation on the graph that's a nonlinear equation. One of the reasons the Fokker Planck equation is so beloved and expressive across the sciences is that it's a linear equation, and so has very nice properties. And this is something that should certainly be preserved at the discrete level. So basically, this led us to realize that we were going to have to make some compromises. And so what we ended up deciding to do is in order to get the drift part of our Fokker Planck equation, we're going to use this Wasserstein gradient flow structure. In order to get the diffusion part of our Fokker Planck equation, we're just going to use the kind of Coifman and Lafon's version of the Laplace-Beltrami operator. Incidentally, that does have a gradient flow structure with respect to this type of Wasserstein metric, but you can see how it's a little unsatisfying. It's like different parts of the equation have gradient flow structures with respect to different notions of the Wasserstein metric on the graph. This is unfortunate, but at some point, just discrete space is different from continuum space. Of course, these things kind of all coincide in the continuum, and maybe things are just a little bit different at the discrete level. Okay, so in this way, like I said, we're able to use the gradient flow structure of the drift to define a drift equation on the graph. And we're able to use the Laplace-Beltrami operator from Coifman and Lafon to add a bit of diffusion to these dynamics. This gives us our graph Fokker Planck equation, where here beta is interpolating between beta equals 0 is pure diffusion and beta equals 1 is pure drift. And we can identify kind of a formal continuum limit of this, which coincides with the original Fokker Planck equation and doesn't degenerate as beta goes to 0 and 1 and allows for flexibility in the choice of this external potential. Okay, so now let me close by showing you some numerical examples of how this can be applied in the clustering context. So in all of these simulations, I have I've given a probability measure Q. I take IID samples of that, and I consider that to be my data set. I construct a weighted proximity graph on that data set. I also choose a kernel density estimate for my data set, which is just, for simplicity in all of the examples I'll give, is given by a Gaussian mixture where the variance of the Gaussians is delta. One thing to notice is that while for both here the weights of the graph and the kernel density estimate, I choose my function eta to be the same, it's just a Gaussian, my connectivity of the graph epsilon can be different from my kernel density estimate. So once I have all of these parameters in hand, I can tell you what our clustering algorithm is. It's a very simple algorithm. Basically, you choose all of these parameters. You have your data points, you choose your graph connectivity, your kernel density estimate parameter, that time parameter that we were discussing earlier, the number of clusters that you want, and the transition matrix you have in mind. In particular, I'll be focusing on this choice Q beta, where beta is 0 is pure diffusion and beta is 1 pure drift. And then we define our embedding function just to map the ith data point to the ith row of the matrix exponential. And then once we've done this embedding, we then apply k-means to the embedded vectors with a specified number of clusters, and that gives us kind of the resulting clustering of our data set. Okay, so on one hand, this is sort of all of the hard work went into designing this transition matrix, and once you have it, sort of the way you use it for clustering, we're doing it in a somewhat naive way. So here are some examples that show some of the behavior of the method. So first, let me talk about what happens if we're in the pure drift case. So this is just mean shift on the graph, and contrast this with the classical mean shift. So suppose that our data set looks like this. So it's sort of these two lines. A human would find it very easy to group these into two groups. So in classical mean shift, what do? We take a kernel density estimate and we move the points around according to gradient ascent of that kernel density estimate in the ambient space. So if we take a kernel density estimate of this with a small bandwidth, then we're going to probably have a lot of local maxima in our kernel density estimate, and it would be a kernel density estimate in R2. So I should properly be kind of drawing the level sets of it. So okay, maybe this is one level set, and this is another, and this is another, something like that. And then we would do gradient ascent in the ambient space. We can see that when we allow these points to move around in the ambient space, it doesn't really disentangle the data very well. And that's just because we have sort of a lot of local maximizers of our density estimator in the horizontal direction, because it's sort of flat in that direction. On the other hand, if we make the bandwidth in our kernel density estimate too big, then the level sets of the kernel density estimator start to look something like this, like the two ridges just merge, and all of the data points are just sucked in towards the middle when they do gradient descent, and it disentangles the data even more poorly. Okay, so we see that classical mean shift, which is occurring in the ambient space, performs very poorly on this data. Okay, what about graph mean shift? This was our new method, but for now I'm saying what happens when we set beta equal to 1, so we have no diffusion, just drift. Well, again, if our bandwidth is too small, we still have a lot of local maximizers. And now, though our dynamics are constrained to the graph, here the color shows you where mass ends up after a certain period of time. It still is not disentangling the data very well. Now, if we pick a much larger bandwidth, the graph mean shift does perform better. Here we do really see that all the points on the top are drawn here and all the points on the bottom are joined there. And this is because graph mean shift, they can't merge in the middle since they're constrained to lie on the graph. But the problem is this makes the situation seem better than it is. Because if I add in even just a tiny bit of noise, oh, sorry that my picture is still on top. If I add in just a tiny bit of noise, it breaks this nice behavior. Okay, so the moral of this slide is that both mean shift in the ambient space, classical mean shift, and mean shift on the graph can give you bad results. They can be very sensitive to the choice of bandwidth in your kernel density estimation, and they can be sensitive to noise. And so here is where you start to see the behavior of this sort of graph Fokker Planck start to shine, and why it's so nice that we're able to take beta very close to 1, adding in just a little bit of diffusion to overcome these problems, while still preserving a lot of the benefits of a density-based clustering method. So here, for lack of time, I'm just going to focus on this top row. So here we see our data sets. That's given by the location of these dots. And I want to cluster them into two clusters, k equals 2. And what I've colored the dots according to which cluster the algorithm maps them to. And we see here the different choices of beta. So this is pure mean shift, no diffusion, doesn't do a good job. Just a little bit of diffusion clusters them very nicely, and a lot of diffusion. Now we see this is really clustering just based on the geometry of the data set. It's treating it as all as one big connected component and clustering it into two by just slicing it down the middle. Okay, so it doesn't give us kind of the desired results. Now, a fair criticism of this simulation might be that I picked the connectivity of my graph too badly for the spectral methods. But what this simulation shows, again, just looking at breaking it into two clusters, is that I can look at a range of connectivity parameters of how I'm constructing my graph. And for the largest range, I see that my graph Fokker Planck, just a tiny bit of diffusion, performs very well. And okay, eventually, if I get epsilon very, very small, spectral methods start to give me something more reasonable, but still not that great. And then kind of here, I just wanted to close showing that as you interpolate between diffusion and drift, you really can get a phase transition in your clustering, whether you're clustering based on geometry or density of the data. But maybe this is what you want, because on some level, yeah, there maybe isn't always a right answer in terms of, while these simulations seem to indicate you should always choose beta equals 0.95, like always be clustering based on density with just a little bit of diffusion. Here, I would argue that it's a little bit more complicated than that. There's some modeling assumptions built in. Okay, so sorry that I have run so long. So I'll conclude here, just showing the slide for future directions. And thank you very much for inviting me to speak.
Thank you so much. Very, very interesting talk. Any questions? Audience, any questions?
Yeah, I had a question. For the kind of hyperparameters in these methods, the bandwidth and connectivity, in sort of more realistic applications, is there some domain expertise that would help guide